Hi, last time we learned about rational exponents and we sort of understood this rule here where we can take any base, raise it to a rational exponent, m over n, and we can think of the denominator as essentially the root and the numerator as essentially the power. And so we can convert this into some kind of combination of roots and powers. That's how we looked at rational exponents, but I'm here to tell you there are some dangers when doing this, and that's why we have all of these extra conditions associated with it. So let's look at what these conditions are actually talking about. So for this bottom one here, we're saying that if the denominator of this rational exponent is even, then we require the base to be not negative, right? It must be greater than or equal to 0. And let's just run through why this must be true. So first, let's take a look at a negative number raised to a rational exponent where this is now odd, okay? So this should be okay. This is not an even number, it's odd, so it should be okay. What does this equal? Well, this is the same as the cubed root of negative 8, and that's going to equal negative 2, right? Because negative 2 cubed equals negative 8, right? Negative 2 times negative 2 times negative 2, negative 8. This is going to be okay, okay? So we're not worried about this one. But now let's try a negative 4 to the power of 1/2, okay? So now we've got an even number here in the denominator of the rational exponent, and this rule is telling us that's even. We require the base to be not negative. We have a negative base. What's that going to give us? Well, that's going to give us then the square root of negative 4, and that's a problem because we cannot take the square root of a negative number. There's nothing here that works, right? Negative 2 times negative 2 gives us positive 4. 2 times 2 gives us positive 4. There's no number you can multiply with itself to give you a negative number here. And so this even root, turns out this is going to give us an undefined answer, okay? And that's why this condition here is there. For even denominators, we require a non-negative base, okay? So that's the first one. That's okay. Let's take a look at some of these other conditions. All right, let's take a look at this top condition here. So it starts off saying m over n in lowest terms where m and n are integers. Okay, they're integers because the definition of a rational number is a ratio of integers. So that's what we're doing here. We're using a rational exponent. And finally, we have this condition where n must be greater than 0. Okay, n must be greater than 0. Why is that? Well, let's imagine you have a number. How about 16, and we're raising it to the 1 over negative 2 power. Okay, so we're saying n is negative 2 here. What would happen here? Well, we could write this as sort of the negative 2 root of 16, but this sort of by definition is going to be undefined, okay? So it just turns out that when we sort of define radicals, if you ever have a negative index, well, that doesn't work, okay? So we don't define radicals with negative indices, only with positive indices. So this is going to be undefined. But you could sort of see how we could deal with this. Instead of putting the negative in the denominator, right, you essentially take it out of the denominator. And so a better way to deal with this is to treat this as 16 to the negative 1/2 in general. And this we could treat as either the square root of 16 to the negative 1, or we could treat this as the square root of 16 and take all of that and raise it to the power of negative 1. That would work, right? So this is sort of the proper way to deal with this kind of operation. If we do this, of course, this top one, we'll get the square root of, well, 1 over 16. That's what that negative 1 does, and this would give us then a value of 1 over 4. Okay, so that's what we get here. Here we could do the same operation. The square root of 16 is going to be 4. 4 to the negative 1, well, that's just 1 over 4. Okay, so this is sort of the proper way to do this. We don't put the negative sign in the front in the index, right? We leave it outside and put it in the power part, in the numerator. Okay, so that's how we're going to do that. Let's take a look at the other part of that condition next. Now, this last part is probably where the greatest danger lies. We're going to be talking about this idea of having the ratio or the fraction there in lowest terms and why that is an important thing to pay attention to. Okay, so let's try this out. In general, this is not going to be an issue if the base here is positive. If a is positive, we don't have to worry too much about this lowest terms part. But if it's negative, pay attention. Okay, so let's look at a negative number then. How about negative 9? Okay, let's say negative 9 to the first power. All right, negative 9 to the first power, what's that going to be? Well, that should just be negative 9, right? That's what we expect this to be. No big problem. This should just be negative 9. But what if you take this and you decide not to leave this exponent in lowest terms? We say, well, that negative 9 to the first power, that's the same as 2 over 2, right? 2 over 2 is 1. Okay, so that must be the same thing. But now look what happens here. We can sort of take that 2 over 2 apart, and we can treat this as like the square root of negative 9 squared. Or we could treat this as the square root of negative 9 quantity squared. That's a valid interpretation of this rational exponent 2 over 2, isn't it, right? So if we do this first one, what do we get? Well, this negative 9 squared is going to be squared first, so that's going to be the square root of 81, and the square root of 81 is 9, positive 9, right? But positive 9 is not the same as negative 9, so we get a different answer here. And instead, if we did it the other way, what would we get? Well, here, the square root of negative 9 first, that's straight up undefined, isn't it, right? We can't take the square root of a negative number. And so look what happened when we did not leave this rational exponent in lowest terms, instead, multiplied top and bottom by some number, you get very different results. Okay, so this is where you have to be careful. If you have something in its lowest terms, don't imagine, multiplying the top and bottom by some number. Don't make it bigger than it has to be. You will get different numbers. Now, there's also another way that this lowest terms rational number can become a problem. So let's take a look at that. All right, what I want to do now is I want to look at another example of sort of a negative base. In this case, let's take negative 8 and we'll square that, and then we're going to raise this to a 1/6 power, okay? So we've got a rational exponent there, a 1/6 power. What do we get? Well, negative 8 squared is going to be 64, and 64 to the 1/6 power, well, that's really the same thing as the 6th root of 64. And if you do the arithmetic, this is going to be 2, okay? Because 2 raised to the 6th power is equal to 64. Okay, perfect. That's what we get here. Now, what if I take these two exponents and I swap the order around, okay? So I do a slightly different operation. I'm going to do negative 8 to the 1/6 power, and then I'm going to square all of that, right? So this is essentially taking the 6th root of negative 8, and then I'm going to square that. But notice what happens here. This is now an even root of a negative number, which is going to be undefined, right? I can't take the square root of negative 8. I can't take the 4th root of negative 8. I can't take the 6th root of negative 8. There's no way to multiply an even number of some number and get a negative number out, right? So that's undefined. Okay, now why is that important? Because if you were to take either of these and use exponent rules to simplify what this is, look at what you're going to get. Right? Take this or take this and use exponent rules. We're going to get negative 8 raised to the 2/6 power, right? So now we have to be careful because we've kind of lost the order of operations by making this simplification. And if you were to simplify this further, look what you would get. You could simplify this fraction and you would get negative 8 raised to the 1/3 power, right? 2 over 6 is the same as 1 over 3. And if you were to operate now with that, you would get the cubed root of negative 8, which is negative 2. Negative 2 is not positive 2. It's not undefined. And so what we've done now is an oversimplification, where we've kind of lost information and we've actually changed what the result is going to be. So these exponent rules, they work, but you have to be careful and always refer back to the original operation here, right? If this is a negative number, a negative base raised to an even power, you know you must get a positive answer out. There's no way you can get a negative number out there. This is an oversimplification. Likewise, if you're taking a negative base raised to a 1 over even number or an even root, you know you will always get undefined, right? And so by combining these exponents together with exponent rules and simplifying it out, we're kind of oversimplifying it here. And you only have to be careful if you have a negative base here. If this was a positive number, everything would be the same, right? Everything would just be 2. So with negative bases, be careful when you're dealing with simplifications of these rational exponents. Okay, hopefully that helped you out. Next time, we're going to be looking at some practice problems where we get to practice using all of these rational exponents. Going to be interesting. I'll see you there.